In this video, I'd like to introduce to you guys the idea of a vector field, and we will start by just thinking about the notion of a function in Calc 1. So let's suppose that f is a function of one variable, and let's think about how this works, okay? So the idea is that f takes in an input. This input can be thought of as an x value, and it assigns to each input an output, a number, just a number in this case. And so for every input here, we get back an output over here, and the output on the right hand side, so in the y domain, this is usually called f of x. That's the y value, y equals f of x, and that value is measured from the origin. So that's measured from, if this is 0, that height right there is how we interpret the value of this. And usually what we do is, if we want to represent this function, so in this picture the blue arrow is the function here, if we want to represent this function, we sketch its graph. And so what do? Well, above each point in the input space, so above each x value, we put the height of the corresponding point in the y direction. So maybe that one goes here, etc. And as we map these, as we pull these points back over here, one way to think of this is instead of just mapping the points, we can attach an arrow or a vector, right? A vector, we can pick up this vector here and we can move it over and just attach it to the input point here in the x-axis or the x-plane. And if we continue this for every point, we'll see that the points, so the input points and the output points, usually trace out some kind of a curve. And in calculus, we usually want this curve to be continuous or something. And then we call the graph over here, we call this graph y equals f of x. And we think of course, we think of this graph as living in the xy plane. But in reality, what is the function doing? It's assigning to each input, each x value, it's assigning a vector, a height, okay? It's assigning a height in the y direction, and we can think of that height as a vector. So a vector that points straight up. So in some sense, we know that the direction of this vector is always either straight up or straight down, and it just assigns a height to the function. So this is the simplest example of a vector field, a function that we're used to of one variable which spits out, one number. So it takes in one number, gives back one number, and we can just regard this function as a vector field if we think of it this way. So what we want to do now in the Calc 3 sense is we want to generalize this idea so that the domain of our function is actually a region in n-dimensional space. So let's generalize this idea now to vector fields. And a vector field is just going to be a function. We're going to call it capital F, and I'm going to draw the two-dimensional picture because, as we know, my drawing is not great. But it's a function f of xy in this case, so it takes in a point in the xy plane, and the output is going to be a vector in the same dimensional vector space. So in this case, it's going to give us back a vector, p of xy, q of xy. So I'm, in some sense, parametrizing the components of the vector output with respect to the point that was the input. And again, the picture, the philosophical idea here remains the same. So we've got some domain that our function f is defined on, and at every point in the domain, so this point will be like x comma y, what does our function do? Well, it assigns to this point a vector that lives in this case, two-dimensional vector space. Okay, and so now we need to be careful about identifying vectors and points. So our domain space is a subset of R2. It's a region in the two-dimensional plane, and the output is a vector in two-dimensional space. Except this vector is not restricted to live as a vector, at least, to be inside of D. So this vector might end up being a vector. So the vector output might end up being, say, this one. So this vector here, this would be f, in this case of xy. And this vector lives in the vector space that I'll call v2, just to keep it straight that it's not r2, but these are two-dimensional vectors. And then the way that we're going to think of this is exactly the same as we just did over here with our function of one variable, and that is, okay, we've got all these output points. Here we've got our vector, that's the output, but let's attach that vector back in the original space, let's attach that to the point that it came from. So we can just pick up this vector and think of translating it over so that it is attached at the point in the domain that it came from. And so at this point, these two, the point and the vector, live in the same plane, and the vector is being thought of as being attached to the point. So this is our vector now, f of xy. That's the output of our function. And the reason this is called a vector field is because for every input, every point in the domain space D here, for every point, our vector field is going to spit out a different vector. And so we can think of this function capital F as attaching a vector at every single point, and I'm drawing these all kind of going out of this space, but they don't have to. So this function can do, the vectors can behave any way they want, and this is the idea of a vector field now. So the inputs are points in two-dimensional space, the outputs are vectors in two-dimensional vector space. Okay, and then of course this can be scaled up to work with three-dimensional spaces. So the domain can be three-dimensional points, and the output can be three-dimensional vector. Alright, so what's a vector? So this is the kind of general philosophical idea of a vector field. Let's very quickly write down some examples of vector fields in physics or in nature. Any kind of force field is a vector field. So some of you have taken physics, and you'll know that any force can be represented by a vector. So any force field is a vector field, and of course that pertains to the gravitational field. So gravitation or gravity, electromagnetic fields, etc. So any kind of force field, and any kind of flow or velocity is also a vector field. So these are the other good examples. So I'll just write velocity fields. Velocity is a vector, and one of the prime examples of a vector field is like flow through a blood vessel. So we'll call this a fluid flow, and so I'm not going to work out the details. We'll do this later on as an example, but one idea is that it's been modeled that flow through a blood vessel, if you take a cross section, the vector field is stronger in the middle of the vessel, so further away from the boundary. And as you work out toward the boundary, friction slows down the flow of the blood, and so the vector field that represents the velocity is rotationally symmetric, and the flow, the magnitude of the velocity is stronger near the center of the blood vessel. So this is just an example in picture, but we'll get back to this one. So any kind of fluid flow or force field that can be modeled by a gravity, So any kind of velocity, including like a blood flow, like this example, or maybe just wind, or any kind of force field, gravity, electromagnetic force, any kind of force can be represented as a vector field. So these are just some examples that we can keep in mind moving forward.